So the first lecture is about signal classifications. So some feedback from previous lecture. Okay, the overview of that we're going to talk about the signal classification. This lecture, signal operations, which is next lecture is going to be the convolution and autocorrelation and correlation. And Fourier series next lecture, Fourier transform, property of Fourier transform, sampling and discrete time, signal classification, impulse response, Laplace transform, discrete time sampling, and further on Z transform. This is the first class, and this is signal operation, Fourier series, Fourier transform. Property of Fourier transform. There is going to be a class test on odd week and the promo class on even week and the promo class on odd week. Sampling and discrete time is going to be on week 6. System classification is lecture 7 and lecture week the week 8 we're going to talk about impulse response. It's mainly about this one, how the output related to this one. And signal classification is and the Laplace transform is trying to going to F domain, and the discrete time signal processing is different from all of them, and for the Z transform is related to discrete time. And then revision class and time preparation. This week we're going to talk about module overview, signal classification, elementary functions, promo class, promo shift. And the engineering signal is a variation of measurable quantity that conveys information about the behavior of the system. So it's a variation of measurable system. It conveys information about the behavior system. Signal can depend on signal variable on many variables. For example, the time, the horizontal and the vertical position as moving image. And this lecture will only talk about the signal related to time. So only related to time. This is the signal here is just ft. Okay, this is only time. And what is system? System is formally defined as an entity that manipulates one or more signal to accomplish a function. And the examples of the practical system, the communication system, control system, motor researching, ordinary system, biomedical signal processing control system. So we interpret signals to make decisions. Signals are transmitted allow us to see, hear, and feel and act. Information are carried in the signal. Signal analysis always allow us to understand and interpret an aspect of signal which is significant but is not obvious for the first observation. Signal analysis always allow us to understand or interpret an aspect of signal which is significant but it is not. It allows us to understand to interpret signal analysis to understand or interpret the signal, but it is not obvious for the just something related to the frequency. And so the signal, the system, and decision. This is the key idea here. We need to think about signal, input the signal, going to a system, trying to interpret, make the decision. And then we are going to talk about the classification of signals to determine what are the analog, what are the digital, what are the deterministic, random, periodic, non-periodic, continuous, discrete, power, and energy. So analog and digital. An analog signal can take infinite number of possible values, and digital signal can take can make up from finite number of values. Can take and can make up finite of. So it can. I mean, this take is the y. So, and for example, the behaviors of is just like maybe the high fidelity, and the human's voice. And this one is the performance is different in terms of the bit error. The key thing is that when you look at the signal, what if it's like that? So there is infinite value in the y. It is analog. However, what if it is what if there are finite value? This value, this value, this value, this value, and this value, this value, this value, this value, this value. So it's finite. So it is worth noticing that CD, this one, is or DVD is discrete. I want to make sure is the CD or DVD the finite or I thought CD is continuous, but DVD is let's see. Let's check whether it is so CD contain I will talk it on the discussion board. So go to the discussion board. Sorry, I'll go to the discussion board. Discussion board. The many discussion. But it's fine. I will keep on catch up. I can do that. Yes, I can do that. And where is the discussion board? Okay, start the chain. Is CD analog or digital? I think it's analog or digital, right? It's analog or digital. Let's keep on doing that, okay? Analog. Digital. Okay, this is about what are these whether the CDs and DVDs are they analog or digital. Okay, cool. So let's continue talk about that. Okay. So let's continue talk about that. Okay. So the analog and digital is just like if there are plenty of if they are infinite, they are finite. They are infinite values, but they are finite values. Okay, and the signal classification can also be determined through whether it is a continuous time signal or discrete time signal. This is related to the x dimension. So, continuous time signal exists at each and every distinct time. It can be interpreted as a function of continuous time invariance, and x is continuous. Discrete time signal only exists in a particular moment of time. T is not continuous. We have discretized. For example, so this is there are finite values in the t, but there is only there is infinite values. There is infinite values here, but this is finite values here. Okay, let's continue talk about the continuous and the discrete time system. The xt is a continuous time signal if it is defined for all values of t. Discrete time signal is derived from a continuous time signal by sampling from a uniform rate. Uniform rate is very important. Uniform rate. This discrete time signal can be analog, and digital time signals can be continuous. For example, the discrete time system can be analog, which is to say analog is just there are infinite. So for example, let's see. So this is a discrete time signal can be analog. For example, it is going to take infinite values. So this one is, and what if it will keep on, since t is infinite, and we are sampling in a constant period. So there is going to be infinite values here. And the digital signal can be continuous. For example, a digital signal can be continuous. For example, this one. This is continuous. This is a digital, because there is only infinite. This is only finite, and it is continuous, just like that. So the discrete time signal can be defined as nt equals to xt ts. Ts is the sampling period, and it's very important concept. Ts is the sampling period, n is an integer, and just like that. And it's worth noticing that what if we use the square bracket denoting the discrete time signal. And even an old signal is at continuous time. What if it is n minus t is xt for all t? Then it is even. And what if it is x minus t then equals to minus xt? Then it is old signal. And the periodic or non-periodic, that is, what if it is repeated itself, xt equal to xt plus t? The fundamental period is the smallest value of t that satisfies the fundamental frequency is the xt. This is a very important thing here. What if the frequency t equals to r pi divided by omega? And what if it's a triangle signal, f equals to t? This will lead to a hertz in the notation. this will lead to hertz. But what if the frequency is notated as the frequency can equal to the omega? You know, omega is how fast you rotate this. The faster you rotate this angle, the frequency is very high. The frequency is just how many times will you rotate for your unit of time, and the f can be equal to omega if the unit is called RAD per s. RAD is just to measure the degree. Another way to represent the degree. So let's talk about whether it is periodic or non-periodic. So this one is non-periodic, and this one is periodic. This one is periodic, but this one is also periodic. And what if when we are adding two signals with T1 and T2, it is periodic only if T1 plus T2 is a rational number and the period with lowest common magnitude of T1 and T2. Then what if it's 102, 103? The T1 equals to T2 equals to the T total is going to be 1. Yeah. This is because 1 divided by e divided 2 is 2. 1 divided by 1 is 3 is equal to 3. So this is the key thing. So the deterministic and random, a deterministic signal can be represented as a mathematical equation. The random signal cannot. The causal signal has 0 value before t equals 0 because t cannot be minus, right? And the deterministic or random signal. So this is deterministic because you can write the equation, and the random is I cannot write the equation. The energy signal and power signal is that the energy signal which will be finite energy, and zero average power. It's zero average power because P is equal to be W divided by T. W is kind of energy and T is infinite. This is a constant. T is going to be 0. It's going to approach to 0. And the infinite, the power signal is going to be finite energy because E equals to PT. P is a constant. T is infinity. So it's going to be infinite energy. The finite power means P equals to E. The reason why it is finite power is that nothing can be infinite power because it is the law of nature. And the energy and the power signal, the total energy of a continuous time signal is the integration of x squared from minus infinity to. You can think about W equals to U I T, and what if the signal U is the signal x here, and this you can see. So y integration. So y integration. So okay. So I see. So the thing here is that the t is the u is a constant, right? The u is a constant. It's not changing. And we also know that what is the u from t, the square is going to be the energy, right? It's going to be the energy of the, you can imagine that. The power of the periodic signal of the foundational is the functional t is just going to transfer it p equals w divided by t, and w is going to be here, and we just want it at specific t, which is going to be 2 divided by t, and the x squared t dt. It is just trying to make a sampling period, a sample period. And then we're going to talk about energy signal and the power signal. The case of discrete times x and the total energy is going to be the summation from minus infinity, n equals minus infinity to infinity, x squared, x n to the power of 2. The average power of the periodic signal with foundational periodic n is that. So the foundational periodic n, is this just the sampling? I want to know what is this n mean? Is this n just the sampling period? N is the sampling. I mean, is it the sampling period? Sampling period. I want to make sure. Okay, cool. So it is only. Why? Why it is n fundamental? Oh, I see. So it is no, not sampling period. It is not sampling period, but it's not sampling period, but it is a foundational period. I mean, you cannot, for example, the discrete is here, okay, and it keep on moving. The foundational period here is going to be, this is going to be n, this is going to be n, and this is going to be, the energy caused by one during one signal, and this is going to be the x to the square. I mean, everyone with the square. Just be careful about the ending values, okay? Just be careful. Do you think you should count this one? I think I should count the. Do we count this one, by the way? Yeah, we do not count this one because it's n minus 1. This is t equals to 0. T equals 0 to n minus 1. It is very important. It is n equals to 0 to n minus 1. So the thing is, this is n equals to 0, and this is n equals to n, and this is the n equals to n minus 1. So it is the summation of the squared of all these values, and trying to sum them up and to divide it by n. And the energy of a signal, find the total energy of the impulse, trying to this rectangular impulse. So the rectangular impulse, we can write this is going to be an xt dt, and this is going to be the this is going to be the, I can find the divided by 2 the a squared dt, and this is going, just the a squared times, just like a squared times t. The key thing is that this is just the kind of the u, okay? This is kind of u, and u, yeah, right. It's just the so the energy of a discrete signal, find the energy of that, okay? So the thing is that it is just so the energy of okay. So let's see. So this one is 1, 2, 3, 4, 6, 7, 8, 9. Okay. So the energy, okay, the total energy going to be 1 square plus 2 square plus 然后this one going to be divided by times to 2, okay? So how to do that? That is very, square plus 2 square plus 3 square plus 4 square. It's going to be 1 plus 4 plus 9 plus 19. It's going to be, this one going to be 20. This is 20, 90, 30. 30 times 2 plus 25. It's going to be 85. Okay, cool. So the elementary function is unit step and unit ramp and unit impulse. So the unit step here is it is what if t is less than 0. So what if t equals to 0? It is 1. Okay, this is very important. Unit ramp is what if t is less than 0. It is what if t? This one does not matter because when t equals to t is 0, it is 0. Unit impulse is that it is t equals to 0, it is that, or it is otherwise. So unit step is the unit step is the integral of an unit impulse. Unit step is the integral of unit impulse. For example, the thing is that the area here is the unit impulse. Is that this area is equal to 1. The unit impulse is the derivative of the unit step. Is that that's first time. The unit step is the integral. How t is the integration of that is always 0, 0, 0, and here we have 1. Okay, it becomes stable. And so what you want is the derivative of this one is always 0, 0, 0. Oh, it's infinity. Oh, and it comes to that. Okay, cool. And then we come to the shifted unit step. This can be shifted or translated, and it just follows the what if you go left, and it's going to be plus, and what if you go left, it's going to be minus, and then how about this? This is let's see. The key thing here, you just plug. You just plug t equals to a, and you must let the signal here to be 0. Okay, so it's just like, because it is this is for evaluation, and how to translate that. So firstly we have this signal, right? Firstly we have this signal. This is ut, and this is going to be u minus t, and it is going to be u minus t 左减 右减 a, okay, 右减, so it's going to be u a minus t. Yeah, just that. Okay, just that. Okay, and 右减嘛. Okay, we only do the operation on t. Okay, 左加右减, and the unit ramp. The unit ramp is the integral of the unit step. The unit step is the derivative of the unit ramp. Is that the unit ramp is what? Unit ramp is that. Okay, it's going to be that. It's the integration of the unit step. So that's our unit step. It is always t, or it is always 0, but the integration of that, it's going to always to be t, because the area here is always t, so it's going to be t. And the unit step is the derivative of the derivative here is 0, 0, plus it is always 1, so it's going to the derivative of that is always 1 after t is greater or equal to 0. And so what I have learned today, we have learned about the module structure and management, and we learned about signal system. We learned about the signal classification, and we learned about rudimentary function. So Next week, we're going to talk about signal operation. So,